For this next set of examples, I want to talk about a specific type of series called a telescoping series. And a telescoping series is a series where the partial sums telescope or collapse in upon themselves, leaving us with an actual sequence of partial sums which can be easily evaluated. Now, again, that's not something that is common for series, that we're going to be able to find a way to express the partial sums and evaluate them, but for telescoping series, we can. So telescoping series rely a lot on algebra, so we will revisit a few things that we've talked about before, rules of logs, partial fraction, decomp, that sort of thing. So let's just jump right into it. I think telescoping series are best shown with examples, and I'm going to start with this example, but I'm going to bring it over to the side a little bit here so that I have a little more space. So this is actually it's the 11th example in my notes here, and so I'll just keep these ordered. But this is 1 over k squared plus k, and this is from k equals 1 to infinity. Okay, so let's take a look at this particular series. And what we're going to do, I notice right away when I see this series, I do notice right away that it could be factored. The denominator could be factored, and that's kind of giving me a clue as to which algebraic technique I'm going to use. So I notice I could just factor k times k plus 1. So it gives me a factoring, and then I can think about, well, okay, so if that factors, well, then what would the actual partial sums be? Because remember, to determine if we're actually looking for, so we're trying to determine if this converges, determine if this series converges, and to do that, to actually determine if a series converges, we have to look at the limit as n approaches infinity of the partial sums. So that's what we're trying to figure out. Do the partial sums have a limit? That would tell me if the series itself converges. If the partial sums have a finite limit, then that means that the series, the summation, the infinite sum has a finite value, has a sum, has convergence. So what do these partial sums look like? So let's take a look. So what is the nth term actually look like? Well, the nth term is going to be the sum from k equals 1 to n. So we would be looking from k, just remember what S of n represents. It represents the sum of the first n terms in the series. So this is a finite sum of 1 over k times k plus 1. And then we take the limit as that upper bound on that summation goes to infinity. So what does that look like? Well, we could start writing this out, but before we do, what if we thought about how else we might be able to express this? And that's the key here for these telescoping. This is a rational function. It's got two linear factors. Let's think about its partial fraction decomposition. So since we can use PFDs here, let's see if there's a different way that we could express this so that we could see what might happen. So let's come off to the side and let's just take our 1 over k times k plus 1 equals a over k plus b over k plus 1. So let's use a little partial fraction decomposition here and see what we can do. So using our partial fractions, I'm going to jump to black again here. So using our partial fractions here, 1 is going to be equal to a times k plus 1, and b is times just k, and using some special easy values of k here to find a and b. Let's go ahead, plug in k equals 0. If k equals 0, then of course a equals 1, and if k equals negative 1, then b would be negative 1. Okay, so a little side work on that partial fraction decomposition, and we can come back here and we can express our nth partial sum actually as the sum from k equals 1 to n of 1 over k minus 1 over k plus 1. Okay. So now let's actually write out a couple of terms here and see what actually happens. So if our value of k, so I'm gonna literally write out a few terms here, and I'm gonna write out maybe more than we need to see the pattern. So some of you might see the pattern right away, but I will go ahead and write out a few terms here. So when k equals 1, the first term in this partial sum is 1 minus 1/2. and then when k equals 2. The second term in this partial sum is going to be 1/2 minus 1/3. And then the next term, when k equals 3, the next term in this partial sum is going to be 1/3 minus 1/4. And hopefully at this point you're starting to see that there is absolutely, if I drop these parentheses, I'm leaving these parentheses in place because I want to differentiate the terms here. So when k equals 4, the fourth term, when I'm adding up the fourth term in this partial sum, this is going to be 1/4 minus 1/5. And this is going to go on and on and on. And I'm going to come down here just to keep it all on one screen. On and on and on, this is going to go for the partial sums. This is going to keep going on, and then we're going to end up on the other end of the partial sum. And I'm actually going to start at the end when k equals, so the last term that I'd be adding up in a partial sum, where I add up the first n terms. So think about going out to 100 maybe here. Then the last term here in this partial sum is going to be 1 over n plus 1. For the last term, I'm working my way backwards, and 1 over n. So it's 1 over n minus 1 over n plus 1. And then when k equals, and I'm going to go back again a little way so that we can fully see the telescoping here. And so when k equals n minus 1, this is going to be 1 over n minus 1 minus 1 over n. And let's just do one more. Might be a little overkill, but I think it's worth seeing all these terms. Sometimes you do. Sometimes the canceling doesn't occur adjacently, and so you do sometimes need to write out a couple more terms. And so the the k equals n minus 2 term would be 1 over n minus 2 minus 1 over n minus 1. Okay, and so this is what we call, this is a great visual of the telescoping. This is what we call a telescoping or collapsing partial sum. Because notice what happens. This minus 1/2 cancels with this positive 1/2. This minus 1/3 cancels with this positive 1/3. The minus 1/4, the positive 1/4. There's a minus 1/5 here, and I can cross it off because even though I didn't write it, the very next term is going to have a 1/5 in it. So these terms are collapsing adjacently. Adjacent terms are canceling each other out, or they're having terms that cancel each other out. Now, it could be that you might have to skip a term or skip a couple of terms to see the collapsing. And that's why writing it out a little ways can be helpful. Now, going to the other end, you can see the exact same thing happening here. You see the 1 over n, and the term before it had the minus 1 over n. And the 1 over n minus 1 in the term before it has the negative 1 over n minus 1. And again, we don't see a negative 1 over n minus 2, but I can cancel it out because I know that it has to occur in the adjacent term. So I can cancel that out. So notice what has happened. This entire partial sum has completely telescoped down, collapsed in upon itself, leaving us with literally 2 terms for this particular series, this particular partial sum. So we can rewrite this partial sum. This is just S sub n is now just 1 minus 1 over n plus 1. We were able to, and that's not our answer, but it is impactful because we were able to actually express the partial sum S sub n explicitly. And if we can express it explicitly, then we can take a limit. And that's what we need to do in order to show that this series either converges or diverges. That's the whole goal. In order to determine if a series converges or diverges, we have to be able to take the limit of the partial sum. At this point, there are going to be other ways to do it. We're going to build more tools in order to do that. But right now, that's our way to do it. That's our definition of convergence for a series. So if we can write that partial sum as an explicit definition of n, then now all we have to do is take the limit. So now to determine convergence, so we can determine convergence or divergence, we can determine convergence by taking the limit as n approaches infinity of our partial sums. So we did all that work so that we could come up with that definition, the limit now as n approaches infinity of 1 minus 1 over n plus 1. And notice what happens, of course, just using our definitions or our limit theory, as n grows without bound, 1 over n plus 1 is going to approach 0, and this is actually exactly 1. which is a finite value, and we can say that the sum from k equals 1 to infinity of 1 over k squared plus k equals 1, which means, of course, that it converges. Not only were we able to find convergence or divergence, but we were able to show what it converges to, and this converges to 1. Okay, so a telescoping series is one in which we get collapsing in upon itself, and we're able to express that partial sum. So the key here was that we had to be able to express that partial sum explicitly. And that took a little bit of work. We had to apply partial fraction decomposition. We had to write out the partial sum, show the canceling, the collapsing of terms here. And again, the terms here collapsed adjacently, meaning each term next to each other is where the collapsing occurred. But it could be that the collapsing occurs 2 terms over, and you write it out a little ways, and then you see how it actually telescopes or collapses upon itself.